3,200 kilometers. The massive border wall spans a distance comparable to the stretch from the Pacific Ocean in California to the Atlantic coast in North Carolina. When Donald Trump became president of the United States, this project surprised the world. Debates immediately erupted across the country regarding the initiative. Why utilize such heavy materials for the barrier? The environment is tough and dangerous, demanding resilience. Engineers rely on tall steel posts nearly 30 feet high to secure the perimeter. At first glance, it looks like a simple vertical array, but in reality, the posts are set deep in concrete to create an almost unbreakable barrier. One can notice the sheer scale of the steel structure rising against the landscape. But this is just the beginning. The secrets of this huge construction reveal themselves gradually. 851,000 illegal crossing attempts were recorded in 2019 alone. Why did the infrastructure require such a drastic upgrade? United States Customs and Border Protection provided the data regarding the surge. The border acted like a door left slightly open for decades. But this is just the beginning. Construction of the first fences began in the 1990s under President Bill Clinton. George W. Bush and Barack Obama continued to expand the system. At first glance, the barriers seemed secure, but in reality, they were only a few meters high. One can notice how easily the structures could be climbed or cut through. It is visible how the political focus shifted by 2016. Donald Trump transformed the wall idea into a major message. The project moves to a new phase. Almost 1,930 miles is the distance the barrier was planned to stretch along the United States and Mexico border. The initial plan was for a solid concrete wall, but the Department of Homeland Security rejected it to ensure patrol agents could see through to the other side. The final model used tall steel posts known as bollards. One can notice the design's vertical transparency. But this is just the beginning. The first step of construction involved surveying the land. Why drill soil samples at every location? The surface often looks stable to the naked eye. This step allows engineers to calculate exactly how deep the foundation must go to ensure the wall stands firm. It seems simple, but in reality, the terrain presents extreme contrasts. Soft, sandy deserts threaten to sink the structure, while wet clay dominates the Rio Grande areas. In Arizona and California, hard rocky mountains feel like natural concrete. One can observe how the land dictates the engineering. The process is only gaining momentum. This critical survey determines the foundation design for the steel posts. The planning is complete, ready for the construction phase. 30 feet is the sheer vertical height reached by the steel posts that dominate the desert landscape. Why is the excavation phase considered one of the most labor-heavy parts of the entire project? It might appear that simply driving poles into the ground would be sufficient for stability, but without a deep, continuous trench, the structure would be unable to withstand high winds or intentional damage, necessitating a foundation of immense strength. Construction crews are tasked with digging a continuous line between 24 and 32 inches wide, reaching depths of 6 to 10 feet to secure the base. In areas where the terrain consists of soft sand, standard excavators and bulldozers can open the ground with relative ease. However, the majority of the border runs through unforgiving, hard, rocky terrain where granite and sedimentary rock sit immediately beneath the surface. It seems like a simple matter of digging, but in reality, regular machines prove useless against this geology. Crews must deploy hydraulic rock breakers attached to heavy excavators to force their way down. One can notice how the breakers hammer and crack the stone non-stop to dislodge large chunks from the earth. But this is just the beginning of the shaping process. A specialized machine, known as a trencher, steps in to refine the rough cut created by the excavators. These high-power units run on diesel engines generating between 250 and 400 horsepower to maintain momentum. This power allows them to cut through the hard ground at a steady, unyielding speed. The trencher moves in to cut deeper, straightens the trench walls, and crushes any remaining soil and rock to leave the bottom perfectly flat. The camera glides along the back of the machine, where a conveyor system constantly carries loose material out of the trench to keep the workspace clean. Because the trencher operates with such high accuracy, it handles hundreds of meters of trench per day, significantly speeding up the construction timeline. Once the bottom is leveled and cleared, the crew begins installing the reinforcing steel frame. Vertical steel bars and horizontal ties are assembled to form a long steel cage running the entire length of the trench. It is visible how the metal structure sits ready for the binding material to be introduced. The process moves to the chemical phase to solidify the work. A reinforced concrete layer, measuring 10 to 20 centimeters or 4 to 8 inches thick, is poured directly over the rebar frame. This creates a flat and stable base where the steel panels can eventually stand without the risk of sinking or tilting. When the concrete bonds tightly with the steel cage inside, it forms a solid, continuous foundation block. This significantly increases the wall's resistance to pulling forces and twisting, particularly in desert zones, where wind pressure exerts a heavy load. The foundation is now fully prepared to receive the vertical structures. 400 kilograms is the upper weight limit for a single steel bollard post utilized in this construction. Following the completion of the foundation, the site transitions to the critical stage of erecting the main wall components. These elements consist of hollow steel tubes, shaped either round or square, standing about 26 in height, with a wall thickness of 10 millimeters. But this is just the beginning. Why do engineers prefer these hollow structures over solid steel bars? At first glance, a solid core might seem stronger, but the hollow profile serves a dual purpose. It reduces the transport load while allowing for the internal pouring of concrete to reinforce the posts later. Heavy-duty trucks deliver these components from the factory, carrying stacks secured by steel straps to prevent shifting. Upon arrival, mobile cranes or truck-mounted units engage their hydraulics to lift each bundle. It is visible how the operators maneuver the load with care to avoid impacts that could bend the steel. The material is placed in a storage area. The process is only gaining momentum. A temporary fabrication zone is established directly outside the active work perimeter. At first glance, assembling these posts seems like a simple task, but in reality, it requires high-power welding machines. One can notice the electric arcs as workers connect the individual tubes into large panels, typically consisting of 4 by 6 posts depending on the wall width. This modular approach transforms the installation speed. Instead of positioning one tube at a time, the crane lifts an entire section. Transition to the next level. Therefore, the crane places the massive panel directly into the prepared trench in a single motion. One can observe the slow descent of the steel as the equipment lowers it with caution. Even a deviation of a few millimeters at the weld or base can cause the entire structure to lean. Such misalignment would make the final anchoring and alignment significantly more difficult to execute. The section settles into its position. Nearly 1,130 miles of barrier depend entirely on the precision of this single stage. Once the steel panels are welded together and brought to the trench, the construction site enters what engineers consider the backbone of the entire project. This phase involves setting the wall panels, aligning them with absolute accuracy, and pouring concrete to lock them in place. It determines how straight, strong, and long-lasting the structure will be. But this is just the beginning. Large mobile cranes or truck-mounted units slowly lift each panel, which weighs hundreds of kilograms, off the ground. Why do 2 to 3 workers on the ground manually hold guide ropes while communicating with the crane operator? It would seem that heavy machinery could handle the positioning alone, but because each panel is almost 9 meters, or about 30 feet, tall and long, it acts like a giant sail, meaning even a strong gust of wind can make the suspended metal sway dangerously without human guidance. One can notice how the crane operator lowers the panel into the trench with extreme caution. Once the metal settles, engineers begin the most critical task of alignment using laser levels, spirit levels, and tension guidelines, along with their own experience. At first glance, placing a steel plate seems simple, but in reality, even a small tilt of a few degrees can cause gaps or bending. Such a deviation would create a crooked wall, weakening the structure and ruining its appearance. It does not end at this stage. After the panel is in the exact position, workers immediately weld its base to steel anchors or support frames already placed in the trench. These temporary welds hold the heavy panel steady while it waits for the final concrete pour. This measure effectively prevents the structure from tipping over due to wind gusts or accidental impacts during construction. The barrier stands ready for the permanent binding material to arrive. Tens of tons of fresh mixture pour into the trench immediately after the concrete mixer truck or pump positions itself at the edge. The material fills all the empty space between the steel and the soil to prevent the heavy panels from tipping over due to wind or accidental impacts. Workers use tamping rods to settle the dense mass, but this is just the beginning. Why do the crews apply vibrating tools to the wet mix? It seems the liquid would fill the voids naturally without assistance. This mechanical vibration forces trapped air bubbles to the surface, helping the concrete press tightly against every surface of the steel post. As the substance hardens, it acts like a hidden anchor, locking the bottom of the panel firmly into the ground to resist pulling forces. At first glance, this is merely a standard foundation, but in reality, it significantly increases resistance to vibration and attempts to pry the wall loose. In important areas with soft ground or near roads, the crews pour an extra layer extending about 5 feet outward. Transition to the next level of defense. One can notice how this wider foundation pad prevents the soil from sinking or eroding over time, especially after heavy rain. This extension makes digging under the wall much harder for anyone trying to cross. Instead of moving loose soil, an intruder must first break through a thick layer of concrete before reaching the steel posts, making the job extremely difficult and time-consuming. The foundation secures the perimeter structure for the long term. High-pressure streams of water strike the steel panels with relentless force immediately after the sections are temporarily secured in place. Workers direct the powerful hoses across the entire surface to strip away the physical evidence of construction. This washing step eliminates layers of dirt, sand, and mud that have accumulated during installation. But this is just the beginning of the preparation process. Why is such thorough hydraulic cleaning necessary before the painting stage? The panels might look ready to the naked eye, but hidden contaminants remain. The water removes stubborn oil residues and welding slag that would prevent the paint from sticking properly. One can notice how the runoff carries away loose metal fragments left over from the welding process. Operators spray strictly from top to bottom, advancing systematically along each panel. At first glance, this seems like a routine wash, but in reality, the technique prevents residue from settling on the clean areas. Workers carefully follow the geometry of the panels so that water and heavy debris do not accumulate in the corners or gaps. Everything only gets more complicated as the surface must be absolutely spotless. Thanks to this rigorous cleaning, the anti-rust coating and protective paint applied later will adhere firmly. This bond drastically improves the wall's durability and corrosion resistance. Such protection is extremely important for the harsh desert environment where the structure stands. The steel is now ready for the next phase of processing. Razor-sharp edges capable of inflicting deep cuts define the final layer of defense. The steel barrier stands nearly complete in the harsh desert environment, But the physical blockade is not yet finished. Why is the installation of these coiled blades strictly forbidden for civilian workers? It would seem to be a standard construction task similar to erecting the panels themselves. But the high risk of severe injury and specific security protocols demand a different approach. Consequently, military units or border patrol detachments take over the site exclusively. Specialized heavy equipment lifts the dense coils to the crest of the wall, while in difficult terrain, manual installation is required. One can notice how the gleaming metal spirals stretch along the top line. The material is designed specifically to make climbing over the barrier physically impossible without sustaining wounds. But this is just the beginning of the securing process. It is visible how soldiers fasten the wire using reinforced metal brackets and anchor hooks. At first glance, this seems like a simple attachment procedure, but in reality, it ensures the barrier remains immovable even under immense force. Every connection is tightened, so the coils cannot be shifted or pulled aside by anyone attempting to cross. This military-grade addition transforms the top of the wall into an obstacle insurmountable by bare hands. The defense system is now fully operational to stop crossings. 15 billion United States dollars is the estimated sum exceeded by the total cost of the wall and related infrastructure. This substantial figure includes raw materials, heavy transportation, surveillance technology, and labor. After many years of construction, hundreds of new miles of fencing now line the boundary. It is visible how the structure reduces easy crossing points, allowing Border Patrol to control the perimeter more effectively. But this is just the beginning. Why is the financial number still growing? The barrier stands tall against the elements, appearing static. However, necessary maintenance and repairs continue to cost hundreds of millions of dollars every single year. At first glance, the wall seems impenetrable, but in reality, cartels have still found ways to get around it. The structure slows down and spreads out illegal crossings. One can notice the concerns raised about environmental impacts on the desert ecosystem and the Rio Grande River region. Experts argue that the wall affects wildlife movement and natural water flow, and this is not the limit. Thus, while the wall provides benefits, it remains far from a perfect barrier. The struggle along the border continues without a final resolution. Nearly 250 miles is the total length of the defensive walls, stretching along the Tohoku coastline to shield it from the Pacific Ocean. Why did the government invest more than 12 billion United States dollars in this static concrete infrastructure? It would seem that modern emergency alerts and evacuation routes might suffice for public safety. But without physical barriers, walls of water rising higher than buildings would destroy entire towns in minutes, leaving zero time for escape. The massive system runs along the northeastern region that took the full force of the 2011 tsunami. It extends continuously through the prefectures of Aomori, Iwate, Miyagi, and Fukushima, forming the longest and most unified coastal defense line in the nation's history. But this is just the beginning of the engineering challenge. Crews began the monumental task by clearing the finalized route, methodically removing old houses and tearing down damaged infrastructure. One can notice how engineers simultaneously constructed material yards and concrete mixing stations to ensure the supply chain remained unbroken. Temporary drainage systems were installed so that construction could proceed without pause, even during the heavy rains of the season. Tangled power lines and pipelines were excavated and removed to clear the path. Because much of the Tohoku coastline sits on weak, sandy soil, stabilization was critical before any vertical construction could begin. At first glance, pouring a heavy foundation seems straightforward, but in reality, the soft ground requires massive reinforcement to prevent the wall from sinking or sliding. Engineers drilled detailed surveys and installed deep concrete or steel piles To create a rigid skeleton, layers of crushed stone and compacted sand were added to create a solid base strong enough to support a wall tens of meters tall. Everything only gets more complicated. Excavators dug massive foundation pits, cutting into the earth to depths of more than 20 meters to reach stable strata. Near the shoreline, workers constructed temporary retaining walls or cofferdams to hold back the seawater during operations. A base layer of concrete was poured into the excavation, followed by the installation of dense steel reinforcement cages. These formed an extremely heavy and wide foot designed to prevent the wall from being pushed over by the immense pressure of ocean waves. One can notice the assembly of tall, thick rebar cages based on optimized laboratory designs rising above the foundations. Formwork is set in place with precision, and concrete is pumped into the mold section by section. Each block, usually several dozen meters long, is poured, cured, and inspected before being connected to the next, creating one continuous barrier. And this is not the limit. Therefore, protection on the ocean-facing side requires additional engineering solutions to manage hydrodynamics. Crews installed special concrete units such as tetrapods and delos to dissipate the kinetic energy of the water. These blocks are stacked in multiple layers around the base to break the force of the wave before it hits the structure. Some sections feature stepped faces or splash reduction ledges to lower the height of incoming surges. On the landward side, soil and crushed rock are added along with drainage channels to prevent rainwater from pooling behind the concrete. These stretches often include a walkway or inspection road on top. And in some towns, the seawall even doubles as part of the local roadway. Railings, fences, and safety ladders are attached to the structure to allow safe public access. Cranes lift precast concrete blocks onto the outer surface in sections where the seawall needs extra thickness and impact resistance. These interlocking panels are arranged in a tight, uniform pattern to reduce erosion from constant wave action. The reinforced armor layer secures the wall against the elements. Thus, the massive structure stands prepared to withstand decades of pounding from the ocean. Two colossal structures demonstrate the height of defensive engineering. Why build such massive fortifications? It seems excessive. But the United States border wall and Japan's towering tsunami barriers are essential to repel the greatest threats. But this is just the beginning. One can notice the sheer vertical expanse of the concrete shields. At first glance, they are just static walls. But in reality, they embody humanity's fierce determination to survive against the forces of the ocean and the world. The barriers stand firm, ready to endure.